So let's talk a little bit about groups of the periodic table. Now, a very simple way to think about groups is that they just are the columns of the periodic table. And a standard convention is to number them. This is the first column, so that's group 1. Second column, third group, fourth, fifth, sixth, seventh, eighth, group 9, group 10, 11, 12, 13, 14, 15, 16, 17, and 18. And I know some of y'all might be thinking, what about these F block elements over here? If we were to properly do the periodic table, we would shift all of these, everything from the D block and P block all rightwards and make room for these F block elements. But the convention is that we don't number them. But what's interesting, why do we go through the trouble about calling one of these columns, a group? Well, this is what's interesting about the periodic table, is that all of the elements in a column, for the most part, and there's tons of exceptions, but for the most part, the elements in the column have very, very, very similar properties. And that's because the elements in a column or the elements in a group tend to have the same number of electrons in their outermost shell. They tend to have the same number of valence electrons. And valence electrons and electrons in the outermost shell, they tend to coincide, although there's a slightly different variation. The valence electrons, these are the electrons that are going to react, which tend to be the outermost shell electrons. But there are exceptions to that, and actually there's a lot of interesting exceptions that happen in the transition metals in the D block. But we're not going to go into those details. Let's just think a little bit about some of the groups that you will hear about and why they react in very similar ways. So if we go at group 1, and hydrogen is a little bit of a strange character because hydrogen isn't trying to get to 8 valence electrons. Hydrogen in that first shell just wants to get to 2 valence electrons like helium has. And so hydrogen is kind of, it doesn't share as much in common with everything else in group 1 as you might expect for, say, all of the things in group 2. Group 1, if you put hydrogen aside, these are referred to as the alkali metals. And hydrogen is not considered an alkali metal. So these right over here are the alkali metals. Now, why do all of these have very similar reactions? Why do they have very similar properties? Well, to think about that, you just have to think about their electron configurations. So, for example, the electron configuration for lithium is going to be the same as the electron configuration of helium. And then you're going to go to your second shell, 2s1. It has 1 valence electron. It has 1 electron in its outermost shell. What about sodium? Well, sodium is going to have the same electron configuration as neon. And then it's going to go 3s1. So once again, it has 1 valence electron, 1 electron in its outermost shell. So all of these elements in orange right over here, they have 1 valence electron, and they're trying to get to the octet rule, this kind of stable nirvana for atoms. And so you can imagine is that they're very reactive, and when they react, they tend to lose this electron in their outermost shell, and that is the case. These alkali metals are very, very reactive, and actually they have very similar properties. They're shiny and soft, and actually because they're so reactive, it's hard to find them where they haven't reacted with other things. Well, let's keep looking at the other groups. Well, if we move one over to the right, this group 2 right over here, these are called the alkaline earth metals. Alkaline earth metals. And once again, they have very similar properties, and that's because they have 2 valence electrons, 2 electrons in their outermost shell. And also for them, not quite as reactive as the alkali metals, but let me write this, alkaline earth metals. But for them, it's easier to lose 2 electrons than to try to gain 6 to get to 8. And so these tend to also be reasonably reactive, and they react by losing those 2 outer electrons. Now, something interesting happens as you go to the D block. And we studied this when we looked at electron configurations. But if you look at the electron configuration for, say, scandium right over here, let me do it in magenta. The electron configuration for scandium, so scandium, Scandium's electron configuration is going to be the same as argon. It's going to be argon. And then you're going to fill, let's see, we're in the 1, 2, 3, 4th period. So it's going to be 4s2. And then we start filling the D block. These are the D block elements here. And you have to remember, the D block, you backfill. So in the D block, this is going to be now 3s1. So how many electrons does it have in its outermost shell? So once again, its outermost shell is its 4th shell. These are, you could argue, higher energy electrons that, it fills this. These are filled before that, and there are exceptions to this, especially that we see a lot in the D block. But so this is what's, I guess you could say, to some degree, is defining its reactivity. Although in the transition metals, the D block elements. Oh, sorry, I made a little mistake there. This is 4s2 3d1. Let me emphasize that we're backfilling the D block. But these, their outermost electrons they still have 2 of those outermost electrons. And there, once again, are exceptions in these transition metals right here that for the most part are going and backfilling that D block. And so then you go back to once you've backfilled those D blocks, then you come over here and you start filling the P block. So for example, if you look at the electron configuration for, let's say, carbon is going to have the same electron configuration as helium, and then you're going to fill your S block, 2s2, and then 2p12, so 2p2. So how many valence electrons does it have? Well, in its second shell, its outermost shell, it has 2 plus 2. It has 4 valence electrons. And that's going to be true for the things in this group. And because of that, carbon has similar bonding behavior to silicon, to the other things in its group. And we could keep going on for example, oxygen and sulfur. These would both want to take 2 electrons from someone else because they have 6 valence electrons. They want to get to 8, so they have similar bonding behavior. You go to this yellow group right over here. These are the halogens. So there's a special name for them. These are the halogens. And these are highly reactive because they have 7 valence electrons. They would love nothing more than to get 1 more valence electron. So they love to react. In fact, they especially love to react with the alkali metals over here. And then finally, you get to your atomic nirvana in the noble gases here. And so the noble gases, that's the other name for the group 18 elements, noble gases. And they all have the very similar property of not being reactive. Why don't they react? Because they have 8 valence electrons. They have filled their outermost shell. They don't find the need. They're noble. They're kind of above the fray. They don't find the need to have to react with anyone else.